Hello everybody to your channel, Thermal Engineering Concept and Principle. In a series of videos, we are going to describe the method of calculation for the heat transfer coefficient of fluids that passes through pipes. How can we estimate the heat transfer coefficient for fluid flow through pipes in convection mode? Welcome again, my friends and colleagues, for presenting another form of convection heat transfer coefficient in the region of turbulent flow, and how can we predict the convection heat transfer coefficient for such cases where Reynolds number is usually uh, falling in a region which is called turbulent flow. And in this episode, we will pass through some correlations used, and I will present one of my correlations which have been published before in the field of predicting uh, convection heat transfer coefficient in the turbulent flow. And thank you for your support. And let us pass through some of the objectives of the present episode. The main objectives of the present episode are: what's the meaning of turbulent convection heat transfer coefficient um, and its method of prediction? We will take a practical case study for water that passes through pipes, and how can we estimate the heat transfer coefficient for such cases. And finally, we will arrive as usual to the closure of the content of the present episode. Turbulent flow correlations. There are quite good number of correlations that are published and can be found in the open literature. One of the oldest correlations is called Cedar-Tart correlation, which was built in 1936, and it depends on the Reynolds and the Prandtl numbers for limitations and conditions as shown in equation number 1. Then we have Petokov in 1970. Again, this is presented in a form that Nusselt is a function of Reynolds and Prandtl with the effect of viscosity and the length of heat the pipe. And we should mention that the properties or thermal properties of fluid usually are based on T bulk or Tf. T bulk, T sub B, and T sub F represents the film temperature. Then we have Genitsky, that is presented in equation 3a and 3b, depending on the range of Reynolds number. And finally, we have a Tarad correlation in a simple form, in fact, This Nusselt number is a function of Reynolds and Prandtl for water, of course, this correlation, and it has been produced from a bank of data obtained from practical field in surface condenser that is used in power plants. And we have the temperature T sub B equal to inlet and outlet temperature divided by 2. And film temperature represents the T bulk plus T sub wall divided by 2. And all these correlations have limited range for Reynolds and Prandtl number in their application. Now we will take a practical case study of water flow inside pipes. Let us consider the tube as shown in figure 1 that is made of carbon steel with standard dimensions L and D out and D in as shown in the figure, and if water flows inside this tube at 1.5 meter per second, and its length was around 11 meter, and it has been found also that the mean temperature or a bulk temperature was 32.2 degrees centigrade, and the properties were measured at that temperature to be raw, the liquid density, specific heat, thermal conductivity, dynamic viscosity, and finally we have a Prandtl number equal to 5.12. The temperature difference between the wall and the bulk fluid was estimated to be 15 degrees centigrade. The solution usually for fluids that passes through a pipe in a convection mode, we should start from the estimation of Reynolds number inside the tube to find in which region we are dealing with this case, and Reynolds number equal to raw water, U represents the velocity, D sub I divided by dynamic viscosity of water, and it was with substituting the values, corresponding values for these properties and physical dimension of the tube, the Reynolds number was estimated to be 43,112.3. And of course, that will be as a part of convection, turbulent flow. And temperature distribution through the pipe should be calculated as shown. We have the wall temperature T sub wall equal to T water plus delta T wall, and it will be 47.2 degrees centigrade. Then we may calculate the properties at T wall: density, specific heat, thermal conductivity, dynamic viscosity, and the Prandtl number. Then we have another definition which is called the film temperature, which represents the temperature of the fluid adjacent to the inner tube surface, which corresponds to T sub B plus T wall divided by 2, and it was estimated to be 39.7 degrees centigrade, and the properties can be estimated according to this temperature from the steam tables to be density, specific heat, thermal conductivity, then we have the dynamic viscosity, and finally Prandtl number to be 4.36. We may calculate the Reynolds number at film temperature, and we should substitute the properties at T sub F. Then we will get a Reynolds number value of 49,896. These temperatures can be presented in a form of figure as shown. We have the minimum temperature, which represents the bulk temperature, and the higher temperature is, of course, temperature of steam, which is higher than 47.2 degrees Celsius, and the tube wall is higher than the film temperature, and so on. So we have almost 4 levels of temperatures. When we use the correlations as shown in the previous table, we may start with the Rads correlation as presented in equation number 4. Then we have Nusselt number equal 0.02 times 43,112.3 to power 0.8 times the Prandtl number to power 0.5. The Nusselt number will be 230.86, and from the definition of Nusselt number we may calculate the heat transfer coefficient of water to be 6,507.95 watt per meter square Kelvin, and this is the answer by using the Rads correlation. We have Januszky correlation as presented in equation 3b. Then if we substitute the values, corresponding values of the thermal properties in terms of density, specific heat, viscosity, then the Nusselt number will be 241.85, and we may use the definition of Nusselt number to get the heat transfer coefficient of water to be 6,817.81 watt per meter square Kelvin, and from these values we may see that the convection heat transfer coefficient as predicted by Januszky was higher than that of the Rads correlation by a value of 4.5%. We continue by using the other correlations as presented in this episode. Let us use Cedar-Pulse correlation as shown in equation number 1. The Nusselt number will equal to a value that is correspond to Nusselt number equal to 146.9. With the definition of the Nusselt number, we may get the convection heat transfer coefficient of water to be 6,960.1 watt per meter square Kelvin, and this is the final answer by this correlation. And finally, let us use Petokoff correlation as presented in equation number 2. Then we have to calculate gamma at the first step and substitute gamma in the original equation of Nusselt number. Then we will get a Nusselt number to be a value corresponding to 268.71, and this is also is higher than Cedar-Pulse value. And then we may use the general form of Nusselt number to obtain the heat transfer coefficient of water to be 7,684.4 watt per meter square Kelvin, and this is the final answer for Petoff correlation. As a summary, as shown in this table, we may find that Petoff expression predicted the higher value of heat transfer coefficient as compared with other correlations. We may find also Tarrat's correlation predicted the lower value, that is corresponding to 6507.95, and the other correlations occupied the space between the higher and the lower value. And we should mention that the Tarrat's correlation has been obtained from measured data for heat transfer coefficient. Therefore, this correlation, as shown in equation 4, was obtained by the best fit to the experimental data, and it's clear that it predicted lower value since the data collected was from using a surface condenser that is used for a long time, and it seems to be that the scale which is found, or the fouling resistance existed, and it seems to be more practical than the others. It could be used in practical design in calculating heat transfer coefficient of water flows inside tubes. Now, my friends, we have arrived to the final part of our episode, that is the closure. We have passed through turbulent convection heat transfer coefficient, and we have specified its range to be Reynolds number higher than 2300, then it will be a turbulent flow. And we presented some of these correlations, and one of them was mine, and we used it in a practical case study in condensation and surface condensers in power plants. And we have made a comparison between these correlations, and we have some valuable references and resources. You may make use of them and advantage. I will put them in a PDF link in the box below this video, that is the description box. And if you feel that the present video is useful to you and others, please share it. And if you didn't subscribe yet, please subscribe to our channel. And I will see you in other forms of convection heat transfer in the near future, in a new series. Bye-bye.